Today we will be learning some results regarding unbiasedness. So the first result is show that the sample mean is an unbiased estimate of the population mean. So let's have a look at the results. Now let x bar be the mean of a sample of size n, and this is taken from a population with mean mu. See, we are asked to show that the sample mean. Okay, so what is the sample mean? X bar is an unbiased estimate of the population mean, which is denoted by mu. So according to unbiasedness, what is that we have to find out? Now we have to show that expectation of x bar is equal to mu. What is x bar? X bar is equal to x1 plus x2 plus etc. plus xn divided by n, where x1, x2, etc. up to xn are sample values. Now, what is expectation of x bar? This is what we have to find out. We have to check whether expectation of x bar is equal to mu. So, expectation of x bar is equal to 1 by n expectation of x1 plus expectation of x2 plus etc. plus expectation of xn, okay, where xi is a random variable, is a random observation, and therefore expectation of xi will be equal to mu. Now, therefore expectation of x bar is equal to 1 by n into what is expectation of x1? Mu. Expectation of x2? Mu. So you just substitute this in A. Okay. So mu plus mu plus mu plus etc. mu. Now, how much times does this mu occur? N times. So what is your answer? 1 by n into n mu, which is equal to what? Mu. Therefore you can say that x bar is an unbiased estimate of mu. I hope this result is clear. Let's move on to the next result. So the next result is x1, x2, etc. xn is a random variable from a population following Poisson distribution. Suggest 3 unbiased estimators of lambda. Okay, so let x1, x2, etc. xn be observations from a Poisson population with parameter lambda. Now, since this follows a Poisson distribution, what is the expectation of xi? That is lambda. So I is equal to 1 to up to n. Now it is said that we have to suggest 3 unbiased estimators of lambda. So I'm suggesting here 3 unbiased estimators. T1 is equal to x1, T2 is equal to x1 plus x2 divided by n, then Tn is equal to x1 plus x2 plus etc plus xn divided by n. So these are the 3 unbiased estimators that I am suggesting for lambda. Now we have to check whether these are the unbiased estimators. So it should be noted that first we will consider expectation of T1. So expectation of T1 is equal to expectation of x1 is equal to lambda. So this is an unbiased estimator. What about the second one? Expectation of T2 is equal to expectation of x1 plus x2 by n which is equal to 1 by n, expectation of x1 plus x2 which is equal to 1 by n into 2 lambda which is equal to, sorry, this is again 2, I'm really sorry, divided by 2. Yeah, this 2 and 2 gets cancelled, you will get lambda. So this is also an unbiased estimator. What about this? Expectation of Tn is equal to 1 by n, expectation of x1 plus x2 plus etc up to plus xn which is equal to 1 by n into expectation of x1 plus expectation of x2 plus etc plus expectation of xn which is equal to 1 by n multiplied by lambda n lambda. So this n and n gets cancelled, you will get lambda over here. So again T2 and Tn is also an unbiased estimator. Therefore T1, T2 etc Tn are unbiased estimators of lambda. Okay, so now that was the second result. Now let's move on to the third result. You have to examine whether the sample variance is an unbiased estimate of the population variance for a normal populations. So sample variance, what is sample variance? S square, and is an unbiased estimate of the population variance. So what is the population variance? What is the population variance? How will you denote that? Sigma square. So you have to check whether expectation of S square is equal to sigma square. Okay, so the answer, let a sample of size n be taken from a normal population mu sigma, and let S square be the sample variance. We have already seen that. We have already seen that the PDF of S square is f of S square is equal to n by sigma square the whole raised to n minus 1 by 2 multiplied by e raised to minus ns square divided by 2 sigma square S square raised to n minus 1 by 2 minus 1, where the range of 0 lies between, the range of S square lies between 0 and infinity. Now yeah, here there is a denominator divided by gamma n minus 1 by 2, and it is equal to 0 elsewhere. So this is what we have studied in the earlier classes. Now we have to check what our expectation of S square is all about. So expectation of S square is equal to n by 2 sigma square raised to n minus 1 by 2 divided by gamma n minus 1 by 2 multiplied by integral 0 to infinity e raised to minus n square divided by 2 sigma square s square raised to n minus 1 by 2 minus 1 s square ds square. This is equal to n by 2 sigma square the whole raised to n minus 1 by 2 divided by gamma n minus 1 by 2 multiplied by integral 0 to infinity e raised to minus ns square divided by 2 sigma square s square raised to n minus 1 by 2 ds square. So how did I got this? I just clubbed this s square and this s square together so that I got s square raised to n minus 1 by 2. Now this is of the form of a gamma function. So how will you write this in the next step? Now this is equal to n by 2 sigma square the whole raised to n minus 1 by 2 divided by gamma n minus 1 by 2. How will you write the gamma function? Gamma n plus 1 by 2 divided by n by 2 sigma square the whole raised to n plus 1 by 2, which is equal to, just do the further calculations and then you will get the answer as n minus 1 by 2 divided by n by 2 sigma square, which is equal to n minus 1 by n sigma square. So here we get expectation of s square as n minus 1 by n sigma square. So it is therefore concluded that s square is not an unbiased estimator of sigma square. Okay, so again a sub result of what we have studied just above. Note, expectation of ns square divided by n minus 1. I'm taking this into consideration, which is equal to n by n minus 1 multiplied by expectation of s square, which is equal to n by n minus 1 multiplied by, what is expectation of s square? We just got it right now. What is it? n minus 1 by n minus 1 by n sigma square, which is equal to sigma square. So it is from this result we say that ns square divided by n minus 1 is equal to 1 by n minus 1 summation xi minus x bar the whole square is an unbiased estimator of sigma square. So that is an extra result. So the next result, x1, x2, xn, extra xn is a random sample from a normal population with mean mu and variance 1. Show that t is equal to 1 by n summation x square is an unbiased estimate of mu square plus 1. So you have to show that expectation of t is equal to expectation of 1 by n summation xi square is equal to mu square plus 1. So let's have a look at the answer. Since the sample is taken from the normal population, since the sample is taken from the normal population, and what is your normal population? Normal mu 1. Then expectation of xi should be equal to what? Mu, and variance of xi is equal to 1 with regard to this particular case. For I is equal to 1, 2, etc. up to n. Also, we know that variance of xi is equal to expectation of xi square minus expectation of xi the whole square. So from this we will get 1 is equal to expectation of xi square is minus mu square. This implies that expectation of xi square is equal to 1 plus mu square. Again, expectation of xi square is equal to 1 plus mu square. Therefore, expectation of t is equal to expectation of 1 by n into summation xi square, which is equal to 1 by n summation expectation of xi square, which is equal, I hope you know how I got this. I took the constant outside, 1 by n, and also the summation outside, and therefore I get 1 by n into mu square plus 1, which is equal to mu square plus 1. Therefore, t is an unbiased estimate of mu square plus 1. So this was your fourth result. Now your fifth result. Fifth result is nothing but let P be the proportion of defective items that is produced by a machine. Let n items produced by a machine are examined, and a random variable xi is defined as follows. Xi is equal to 1 if the ith item examined is defective. Xi is equal to 0 if it is not defective. We have to show that t is equal to summation of xi, that is t by n is an unbiased estimate of p. Expectation of t by n should be equal to p. We have to show that. Also, we have to show that expectation of t into t minus 1 by n into n minus 1 is an unbiased estimate of p square. So there are two things that we have to show in this problem. Now here in this problem it is said that p is the proportion of defective of items and n is the number of items produced. Xi is the variable and xi is defined clearly over here. Okay, so let's just write down a few things that we got from the question. Now, since the proportion of defectives is p, probability that xi is equal to 1. What does xi is equal to 1 indicate? If the ith item examined is defective. So the probability that xi is equal to 1 is equal to p, and probability that either defective or non-defective. So probability of xi equal to 0 will be what? Yes, 1 minus p. Now, what is the expectation of xi? Expectation of xi is equal to what? 1 into p plus 0 into 1 minus p. This is equal to p. Now how did I get this? Here my values of x are 1 and 0. The corresponding probabilities are what? P and 1 minus p. So when I take expectation of x, what should I do? 1 into p plus 0 into 1 minus p. Right, this is something you have studied in your last semester. So here I get the expectation of xi equal to p. Now I'm going to find out expectation of xi square, which is equal to 1 square into p plus 0 square into 1 minus p, which is again p. Again I'm going to find out variance of xi. What is variance of xi? Expectation of xi square minus expectation of xi the whole square. So this is equal to p minus p square, which is equal to p into 1 minus p. Okay, so there are some results with us. Now what we have to do is we have to take the first question into consideration, the first sub question. T by n, we have to check whether T by n is an unbiased estimate of p. So first and foremost, what is T? From the question it's clear that T is equal to summation xi. So T is equal to summation xi. Then x pot is expectation of T. Expectation of T is equal to summation expectation of xi. What I did is I took the summation outside, which is equal to n into p. I hope that is clear. Therefore, expectation of T by n, this is what we have to check, is equal to 1 by n expectation of T, which is equal to 1 by n into np, that is equal to p. Therefore, T by n is an unbiased estimator of p. We have to just check about our second result that we have to prove. And second result is nothing but we have to prove that expectation of T into T minus 1 divided by this one, T into T minus 1 divided by n into n minus 1 is equal to p square. So let's have a look how to prove that particular result. For that we need variance of T, which is equal to variance of x1 plus x2 plus etc plus xn, which is equal to variance of x1 plus etc to variance of xn, which is equal to n into p into 1 minus p. So where did I get this from? I have here p into 1 minus p over here, which I have found it out a bit earlier, so that I substituted over here, so I get an answer like this. Okay, now we'll have a look at expectation of T square, which is equal to variance of T plus expectation of T into expectation of T the whole square, which is equal to np into 1 minus p plus n square p square, which implies expectation of T into T minus 1 divided by n into n minus 1, which is equal to 1 by n into n minus 1, expectation of T square minus expectation of T, which is equal to 1 by n into n minus 1 multiplied by np into 1 minus p plus n square p square minus np, which is equal to 1 by n into 1 n into n minus 1 into np into 1 minus p plus n square p square minus np. Oh, just a moment. Which is equal to 1 by n into n minus 1 into n into n minus 1 p square, which is equal to p square. Therefore, t into t minus 1 divided by n into n minus 1 is an unbiased estimate of p square. Okay, so I hope you have understood this result. Then regarding the sixth result, see, x1, x2, etc. xn is a sample of independent observation from a Poisson population with parameter lambda. Obtain an unbiased estimate of e raised to minus lambda. So the answer for this result is, let a statistic t be defined as follows. T is equal to 1 if the first observation of the sample is 0. T is equal to 0 otherwise. Now, probability that the first observation is 0 is equal to lambda raised to 0 divided by 0 factorial e raised to minus lambda, which is equal to e raised to minus lambda. Probability that the first observation is some number other than 0 is equal to 1 minus e raised to minus lambda. Therefore, expectation of t is equal to 1 multiplied by e raised to minus lambda plus 0 into 1 minus e raised to minus lambda, which is equal to what? E raised to minus lambda. I hope you have know that how you got this expectation. Now, therefore, t is an unbiased estimate of e raised to minus lambda. I hope this is also clear for you. Now let's have a look at the seventh result. Show that 2x bar is an unbiased estimate of theta. So you have to show that expectation of 2x bar is equal to theta for this particular distribution. Now the answer for this result, let x1, x2, etc. xn be the sample, and what is 2x bar then? 2x bar is equal to 2 into x1 plus x2 plus etc. plus xn divided by n. Then what is expectation of 2x bar? Expectation of 2x bar is equal to 2 by n summation expectation of xi. Then what is expectation of xi from in context of this PDF that is given, that is equal to 1 by theta integral 0 to theta xi dxi is equal to 1 by theta xi square divided by 2 0 to theta, which is equal to what? Theta divided by 2. Therefore expectation of 2x bar, what is expectation of 2x bar, is equal to 2 divided by n multiplied by n theta divided by 2, which is equal to theta. Therefore we have proved that what? Expectation of what? 2x bar is equal to theta. I hope you have understood the 7th